proceed?
Yes, sir.
Yes, sir. Yes, sir.
Go to my, yeah, I'll go to my window. Okay, screen is back again.
Yes, sir.
Everyone?
Visible, screen visible, sir.
Okay, let me proceed. Okay, I'll take maybe up till 1:15. I'll close with that for your lunch. Now, this slide which you see on the screen, it summarizes what we've been talking so far. And in the absence of an explicit integration formula, we as engineers accept numerical integration, which is an approximation. We don't mind it. But that approximation can be improved by increasing the number of segments, or it can be improved by the increasing the order of the polynomial, which also you agree. Okay. But one good advantage, thank God, that it is converging. What I mean by that, I divide it into 100 elements. It gives me an approximate solution. I divide it into 200 elements. It still gives me approximate solution, but better approximation. I divide into 1,000 elements. It still gives approximation, but very good approximation. Increase the number of elements or increase the order of the elements. You have 10 elements which are linear. Increase 10 elements with quadratic, good improvement. Have the same 10 elements with cubic, very good approximation. Still, it's an approximation. So that is called convergence. Maybe if I say the opposite of that, I have 100 elements, I get a solution. I get 200 elements, I get a bad solution. And I get 300 elements, I get a good solution. I get 400 elements, very good solution. I get 500 elements, bad solution. Then it is up and down. You don't know. But good news is it is always converging. Increase the number of elements, increase the order of the polynomial. Solution is becoming better and better and better. That's the conclusion we have made so far. Let me go a bit faster. All right, we are going to look at the case study of a taper bar with the sulfide. Okay, we said constant cross section, the displacement variation is linear. Taper cross section, the displacement solution is logarithmic. Taper cross section with sulfate included, then the solution is becoming highly complex. Now you need to find a solution for this. What is this after all? This is your dining room table. Your dining room table is taper and it is fixed at one end and it is subjected to load at the other end. The solution for that is highly complex. The displacement solution is highly complex. Now, we don't mind an approximate solution. We want to get a good approximation. So I'm going to, at the end of this class, I'll say this is finite element. Okay. So we are introducing finite element like this manner. Now, this is an engineering problem. I told you this is a physical problem. Dining room table, taper leg, including the sulfate. It's a physical problem. Now we are going to find an approximate solution. Just like that, you cannot find an approximation. You have to formulate this physical problem. We have to formulate this problem. We said that we don't mind an approximation provided we have formulated the problem. We have formulated the problem. So now, this taper rod is an engineering problem, it's a physical problem. I'm going to find a solution which is an approximate solution. So I must convert it into a mathematical problem because the solution is mathematical. So I'm going to convert my engineering into mathematics. How do I do that? My engineering is my taper leg, my dining room leg. And I'm going to find an approximate solution because the exact solution is not available. And to get an approximate solution, I'm going to convert my dining room table problem into a mathematical problem. What do I mean by that? I'm going to represent my dining room table by a mathematical equation so that I could find a mathematical solution. I could use the approximation. Good. So how to convert this engineering physical problem into a mathematical problem? You cannot simply say, okay, this dining room table problem is a mathematical problem. I represent it by differential equation. I represent it by logarithmic equation. I represent it as exponent. No, you cannot. How do I do that? I use physics. My students will curse me, sir. We finished the math in the second and third semester. Now you are in sixth semester. You are asking us to go back to maths. Sir, we finished all the math, physics, chemistry with the first year itself. Now you are asking me to come to physics now. I tell you, don't leave the knowledge there itself. Carry it with you. Carry it with you. It will help you. Now it's going to help you. What did we learn in physics class? We said anything which is physical, anything which is physical, it must abide by law of physics. Law of physics. What is the law of physics? The law of physics says a system, a physical system, is under equilibrium. Otherwise, it is not a physical system. If it is not under equilibrium, it will become unstable position. That's not engineering. That's not physical. Anything which is stable is physical. So my dining room table is a physical problem, which is a stable problem. It's not an unstable problem. Okay. So what do I mean by physics stable? The sum of my force to the left is equal to sum of my force to the right. Or sum of my force vertical direction, sum of my force in the horizontal direction is 0. Moment at a point to the left is equal to moment at the right. These are all called as law of physics. So let me take my problem, my dining room table leg subjected to concentrated load and its own self weight. It is under equilibrium because of the physical table. Therefore, the sum of the forces in the vertical direction is equal to 0. So I have taken a small segment dx. I see that I have taken a small segment dx. So if the dining room table is under stable condition, then this small segment is also under stable condition. So sum of my forces on that small segment is equal to 0. I put mathematically sum of my vertical force equal to 0. What is the vertical force? Vertical force upward is sigma. Vertical force downward is sigma plus d sigma. There's a variation in stress. So what is force? Stress in the area. Sigma into A. What is the downward force? Sigma plus d sigma into A. Plus there is self weight. So into volume A into dx. So this equation is the physics equilibrium equation. There is no horizontal force in this case. There is no bending moment in this case. So if the problem is going to have horizontal force, we'll write the horizontal force equation also. The problem is having moment equilibrium also. Now it is only vertical forces are under equilibrium. So upward force is plus dA, sigma into A is upward force. Downward force, sigma plus d sigma into A plus by gamma into A into dx. Okay, I simplify it. Oh, 1 minute, 1 minute, 1 minute, 1 minute. Wait, what happened? Simplify.
So can you
Sigma
press
into A.
hide button, sir? Can you press hide in that, sir?
Which one?
Can you press hide one? Hide nearby stop
Okay.
sharing.
Okay. All right. Thank you.
Yes, sir. Thank you, sir.
So sigma into A is left side, and right side is sigma into A plus d sigma into A plus gamma A into dx. Sigma A get cancelled. Therefore, 0 is equal to sigma A into gamma into A into dx. What is your sigma E epsilon? Stress by strain is equal to Young's modulus. So replace by E into epsilon. So D into E into epsilon into A plus gamma into A into dx. What is epsilon? Epsilon is strain. What is strain? Change in length by original length. Original length is dx. We are talking about small segment dx. So E into du by dx into A plus gamma into A into dx. I'm rewriting that. I'm taking that A inside. So d by dx of EA into du by dx plus gamma into A is equal to 0. This is the equation which defines that small segment is under equilibrium because of the force equilibrium. So the mathematical problem formulated by this equation is representing your dining room table leg problem. Dining room table leg, you have taken small segment and you set that segment under equilibrium. That is represented by the equation d by dx of EA into du by dx plus gamma into A equal to 0. This, we have taken a small segment dx at the midpoint. I take the small segment dx closer to the fixed end. Formula is the same, d by dx of du by dx gamma into A is equal to 0. What is A? A area at that point. All right? At the end where nearer to the load is applied. So your dx will be having an area, tapering area. So area is going to become a function of x. Then I am now writing next governing differential equation is d by dx of E into A of x. Where takes the segment? At that segment, what is the x? Area x. D by dx of A into du by dx plus gamma into A of x equal to 0. This is the governing equation for that segment which is under equilibrium. You can take the segment anywhere, between 0 to L, anywhere take the segment. The same equation, your area at that location, you'll be putting it as a function of A of x. And the next one, very important. Next one, very important. What is it? It is fixed. So this physical problem is representing the equilibrium by the governing equation is having a specific condition called boundary condition. What is the boundary condition? At x equal to 0, it fixed u is equal to 0. At x L, load is applied P, then there is a reaction force. So applied force should be equal to reaction force. What do I mean? A 100 Newton force, P. The reaction developed there must be minus 100. Only if the applied force and the reaction force is same is under equilibrium. If my applied force is 100 and my reaction force 99, what will happen? It is not under equilibrium. It will keep on elongating because there is a difference of 1 Newton. So the boundary condition says applied force must be equal to reaction force. So at x equal to L, what is the reaction force? Stress at x equal to L into area at x equal to L. Stress is E into epsilon. So E into du by dx into A equal to applied force P. This is called boundary condition. So it is not enough if you express a governing equation for the small segment. You have to now define it is valid anywhere from 0 to L. You have to say at x equal to 0, specifically displacement is 0. At x equal to L, specifically applied force equal to reaction force. Therefore, this set of equations, the governing equation d by dx of Ex du by dx plus gamma A of x equal to 0, and the governing equation for the taper problem with a specific condition at x equal to 0, u is equal to 0, at x equal to L, reaction applied force. With this condition, you have to now find a solution. You are going to find an approximate solution for which problem? A taper rod problem, physical, which is represented by this set of equations, governing equation, domain, boundary condition. So this problem is complex. I don't know, now it comes to your mind, you have studied near differential calculus, boundary value problem and initial value problem. Static, if it is dynamic, at time t is equal to 0, at time t is equal to t1. So how does it vary with respect to time? It becomes dynamic problem, static problem and dynamic problem. We have formulated the problem and we are going to find the so the governing equation is d by dx of Ex du by dx plus gamma into x equal to 0, and the domain is between 0 to L, and the boundary condition at x equal to 0, u is equal to 0, and x equal to L, reaction force equal to applied force. Now, for which you are going to find an approximate solution. That is their engineering approximate solution. Mathematics people, immediately let, very favorite word of a math teacher, let us assume, okay, what he or she did, let the approximate solution be u star. Because if you are going to look at the governing equation, it is solution is u. Solution is u. You don't know the u. And you accepted an approximate solution. So you gave the name for approximate solution. When you said let u star be the approximate solution, you have put let it be. Let. U star can be anything. U star can be anything. You can say that the approximate solution U star is sin x. That the approximate solution U star equal to exponential x. That the approximation U star is equal to sin hyperbolic x. You can be anything. But that approximate solution should satisfy boundary condition. You can assume let U star be sin x. So the boundary condition at x equal to 0, boundary condition at x equal to L must satisfy this condition. You have used sin hyperbolic x, but the boundary condition must satisfy. Let U star be exponential x. You can have. But then somebody in mathematics, you may remember his name, you remember Taylor? He said, any mathematical function can be represented by a series. I gave you for log x, similarly exponential 1 plus x power 1 by factorial 1 minus x power 2 by factorial 2 plus x power 3 by factorial 3. So everywhere it is a function of x, a polynomial. So mathematics people said that I write it as a polynomial a0 plus a1x plus a2x squared plus a3x cubed plus a4x power 4 up to an x power n. This is representing anything. According to Taylor, any series solution is an approximate solution. Now, mathematics would say n tending to infinity, but you are an engineer. You don't go for infinite solution. You look for finite solution. So you will go up to 100, a100 x power 100. Then someone else may say, it's only approximation. I'll stop with 10. up to A10 x power 10. One of the smart students will say, sir, we'll stop it with fifth order, sir. Okay. It's an approximation. You agreed at beginning itself. That is an approximation. If I'm willing to do the bull work up till 100, then I get a better approximation. Still, if there's another fellow who is doing the bull work up to 1000, he gets still better approximation. It's still approximation because n is supposed to be up to infinity. Understood? So the best approximation is a polynomial approximation. Okay, I am working out. I stop with cubic now. I am assuming cubic. I know pretty well the solution is supposed to be logarithmic, complex logarithmic, which is the nth order. But I am approximating. I'll approximate a cubic solution. Okay. Now, this approximation is a0 plus a1x plus a2x plus a3x cubed. Okay. If I apply the boundary condition at x equal to 0, u star is equal to 0, because that's the boundary condition, yeah, because it is fixed. So at x equal to 0, u star is 0, what will become? A0 will become 0. At x equal to L, reaction force equal to applied force, EA into du by dx equal to applied force P, one more coefficient will go away. So two coefficients are gone, A0 and A1 with the boundary condition. The remaining is only A2 and A3. So I'm now getting U bar star. U star is the assumed approximation. U bar star, after applying the boundary condition, the coefficient A0 and A1 is gone. So the remaining coefficients are only A2 and A3. So there will be a function phi naught plus A2 into phi 1 plus A3 into phi 2. Okay. This is the approximate solution which I assumed after satisfying the boundary condition. I call that as U bar star, which is the eligible approximate solution. Now, I substitute this eligible approximate solution into your governing equation. What is your governing equation? d by dx of EA into du by dx plus gamma x equal to 0. You remember that? That is a governing equation we had. D by dx of EAX and d by dx plus gamma x 0. Into which I am now substituting my approximate solution. So I'm going to substitute my U bar star. U bar star, I assumed a U star and I apply the boundary condition, I got the U bar star. Okay. I substitute this U bar star into your governing equation. So d by dx of EAX into du bar star by dx plus gamma ax equal to here d by dx of EA into du by dx plus gamma ax equal to 0. Now, instead of u, we are substituting u star, an approximation. Therefore, the right hand side is not equal to 0 because in the approximate solution, it will not homogeneous. There will be error. There will be some leftover. We call it as residue. We call it as residue. Now, this residue came because of the approximate solution. Right? So the residue, your approximation was a good approximation. Larger residue, your approximation is a bad approximation. All right? Now, if you're going to substitute that U bar star into your equation, which becomes a homogeneous equation. So what is happening? The residue equation is now is the function of A2 and A3 because the U bar star is A2 and A3. All right? So your residue is a function of AI. Now, what is your job? Make the residue to be smaller. Make the residue to be smaller. So now you are going to put various permutation combination of A2 and A3. For which combination of A2 and A3 my residue is going to be small. Now that is the best approximation. Still is an approximation, but I am able to find out the A2 and A3, which is making the residue to become smaller. I get the best approximation. How to make the residue small? Mathematician immediately told, for a function to be minimum, what do? Differentiate that function equal to 0, maximum minima theory. So WDI, dr by di equal to 0. Minimize the residue. Okay. Now, there are many methods by which you could do the minimization. And one method is finite element method. Okay. I'm not going to talk about all the other methods. Okay. No time. But at least now you understood. After all, you are finding out an approximate solution. So you are writing the governing differential equation and you are putting a substituting approximate solution, make approximate solution to satisfy the boundary condition, substitute that approximate solution. And there is error or residue. Minimize the residue and you will have your residue to be smaller. And the fifth method is called as the rich method, and that is your finite element method. Okay. I will tell you what is each method, then I'll spend time on the rich method, which is a finite element method. Okay, you have to make the residue to become smaller. Okay, there is a method called collocation method. What does it do? It makes the residue to become small at a particular point called collocation point. Residue at a particular point. You wanted L by 2 and L by 4 to be small residue, then use the collocation method. Or the next method is called subdomain method, where you integrate the residue. There is a residue everywhere. You integrate the residue. Equate the residue to become 0. Error is there, and integral error is 0. Good approximation. Good approximation. Then least square method. You find the square of the residue. Minimize it. The reason is, if you remember your mathematics, common average, geometric mean, x1 plus x2 plus x3 plus x4 by 4 is x bar. That is geometric mean. Instead, if you are going to find out x1 plus x2 square plus x3 square plus x4 square under the square root by 4 is called as RMS value, root mean square value. Square it and find average. RMS value is better than geometric average, mean value. So least square is better than subdomain. Subdomain, you integrate the residue. In least square method, you integrate the square of the residue. Then somebody came, what he did, he multiplied the residue with some function. He named it as weighting function. And he made 0, which gives still better. And the fifth method is this method. He also used Amos-Gallatin method, but the integration procedure is different. And he got the best. And finite method is that rich method. Okay. We will do that. Okay, this is my class notes. Here is the problem with some numerical number, so that when I finally finish my lecture, I would about this numerical number problem. It is still the same taper rod problem. That is a room table leg problem. Okay, for which the length is given, area varies from 80 to 20, Young's modulus, density, and the sulfate, everything is given. And for which the governing equation you already know, dx by dx plus gamma ax equal to 0. And the boundary condition at x equal to 0, u is equal to 0, x equal to L, reaction force equal to applied force. and the area variation is varying linearly. It is from A1 to A2, it is varying, and I fitted a curve A1 minus A2 into X by R. This is the S2, okay, for which I am going to find an approximate solution. So the governing equation is multiplied by a weighting function W of weighting function W, and this is that. And I have gone ahead with some numerical. I think I may not be spending time with that. I solve integral equation equals to x w of x. Now let's have right. Let's look at the left hand side. Okay. Yeah, the left hand, the last line. Integral ex into du by dx into dw by dx. E into a of x. What is du by dx? Change in length by original length. Strain. What is dw by dx? Variation of the weighting function. That's again strain. What is E into strain? The strain is stress. So integral stress into A into dx is dV, volume. What is integral stress into strain? Integral stress into strain is energy. Strain energy. Okay. Let's look at right hand side. Let's look at right hand side. Right hand side is gamma Ax into W of x minus P into W of R. What is P? P is the load at x equal to L. What is WL? Weighting function, displacement at x equal to L. Load into displacement is work done. Work done by the centered load. Similarly, gamma is density, A of x into dx is volume, density into volume is sulfate, into W of x is the variation of the weighting function. So that is sulfate into distance is work done by the sulfate. So left hand side, total work done by all the loads. Total work done by all the loads. There is an error there. The minus sign, it is gamma x W of dx plus P into W of L. Now, what is the equation has now become? The strain energy stored equal to done. Strain energy stored equal to done. If it clicks your mind, we state in a system, the law of conservation energy says that when it is subject to external load, the energy stored inside the system is equal to work done outside. Energy stored inside the system equal to work done outside the system. It's called law of conservation of energy. So now, our RIT method, which was started as an approximate method, we wrote the governing equation and we wrote an approximate solution. We satisfied the condition. We substituted that approximate solution and we minimized the residue. And the minimization equation became energy equilibrium equation of law of conservation of energy. So now, the solution you're going to find out is an approximate solution only. No question about it. But that solution is going to satisfy the energy equilibrium to say the internal energy stored equal to external work done. That is why the RIT method became the treat as finite element method, and finite element method is the energy equilibrium method. Though it's an approximation, but sure that the equilibrium of energy is there. This is why finite element method became the approximation. Okay. All right. Now I complete my exercise. So my approximate solution I assumed was fixed solution. So I accepted the boundary condition x equal to 0, u is equal to 0. So a naught is equal to 0. So the u bar star is a naught has become 0. A1x plus a2 star plus a3x cube. I wrote it's a summation of aj into phi j, a1 phi 1 plus a2 phi 2 plus phi 3. And my weighting function is phi 1, phi 2, phi 3. One is x, phi 2 is x square, phi 3 is cube. So I got my approximate solution, and the approximate solution substituted into the equation, and I got my equation dx into d phi j by dx into d phi I by equal to gamma ax phi I dx plus p into phi I. Left hand side is strain energy, right hand side is work done. P into phi I, phi into phi I, total work done on the right hand side. Now, I got a cubic solution. So I is ranging from 1 to 3, A ranging from 1 to 3. So when I put the integration and it becomes a matrix of 3 by 3, you will get I is 1 to 3, J is 1 to 3. So K1, K12, K13, K21, K3, K31, K32, K33. And right is going to become I is 1 to 3. So R1, R2, R3. So I my Kij and Ri. So phi j, phi 1 is x, phi 2 is x square, phi 3 is x cube. So d phi 1 by dx, d phi 2 by dx, d phi 3 by dx, and shoot them. So I get my k11 0 to L e into a of x, d phi 1 into d1 by dx, k11. So e into a is already derived, 80 minus into x, d phi 1 by dx. Phi 1 is x, so d phi 1 by dx is 1. Again, d phi 1 by dx is 1. Integrate it, you get some number. Similarly, k1 ax into e into a is 80 minus 0.2x. D phi 1 by dx, phi 1 is x, so d phi 1 by dx is 1. Phi 2 is x square, therefore d phi 2 by dx is 2x. And you integrate it, you get similarly k1 3. Similarly, you can have k2 k2 to k2. You get right hand r1, r2, r3, get that integration. So you got now a matrix, K matrix into a1, a2, a equal to r1, r2, r3. You solve and you get a a1, a2, a3. Now, the approximation that you have done is a naught plus a1x plus a2x plus a cube, and a naught becomes, so the approximation is a1x plus a2x plus a3 cube. Now you find the maximum displacement of the 300. You substitute, you got some number. Fortunately, I have the exact solution for this problem also, which is 0.0378. You could see there is an error. But this is the best approximation. If you want your error, you change the error. I'm going to approximation of cubic order, and the solution 0.03306. So you could see that there is an error. In cubic approximation, there is A naught plus A1 plus approximated had 3 for x power 4, A5 x power 5, A6 x power 6. If I have cubic instead of cubic, I got sixth order solution. Now it will be improving. In the sixth order, tenth order, it is still improving. In the 10th order, if we have 50th order, instead of 50th order, if we have 100th order, can you see the improvement happening or the convergence happening? You are improving by refining the polynomial. You are improving by refining the polynomial. All right? If it is clear, I can jump to the next one without any hesitation. You will be able to understand. Now, I have now got the bar of length L. So far I worked out. Now I'm going to divide it. I'm dividing it 3 elements. So how much? L by 3. I divided 10 elements. How much? L by 10. So I'm going to have elemental length, the small le. Total length is L, capital L. Now I am dividing into number of segments. So LE. Okay. So now I'm taking one such element here in the figure. If I'm going to say that it is under equilibrium, every element is under equilibrium. You cannot say one element is under equilibrium, another element is not under equilibrium. No, every element is under equilibrium. So I'm writing now the equilibrium equation for one element whose length is He, whose length is He. Okay. Now it has got the end node I and node J. So I'm writing down the solution or the equilibrium for that element is there I had 0 to L. Now I'm saying 0 to H. E of the element, A of the element, du by dx, dw by dx, writing down the right hand side. Now, I would assume an approximate solution. Now I'm going to assume an approximation for the element. Right? I assumed the approximate solution cubic for the whole domain, and I found how the error is, the error can be, etc. etc. Now I am approximating. Why not I approximate A naught plus J1x? I can, because let. Then you'll ask me, sir, you did not approximate A naught plus J1x there. I can. Now, you are an engineer. You know pretty well the solution is going to be complex logarithmic. If you are going to assume the solution to be linear, then you are crudest. You can assume nothing wrong. Crudest solution. If you make quadratic, better. Cubic, better. It's the solution. But when it comes to the elements, sir, I can divide it into elements, sir. Why should I still assume the element also cubic? I can assume linear. Okay, let me assume linear and let me substitute that. And I have now calculated the values at the node points, two end, node I and J. And okay, this is the final formulation is there. And I assume the shape function and I get a polynomial and I get my K11, K12, K2, K22. Here you have a 2 by 2 matrix because you have node 1 and 2 or node I and J. So you are able to find out the K matrix for that element. You are able to find out the K matrix for that element. And the K matrix for the element 1, element 2, element 3. Now you need not divide equal length. Now, of course, I have shown you here with equal length. It may not be equal length. Okay. And you put that element at length He and you calculate your K matrix for each element. So you have divided them. In our case, we divide them into 3 elements, and we have calculated the stiffness matrix of each element. Now I'm doing assembly. When I did the assembled, now I will the same common node between element 1 and 2. I'm not cutting them. I'm just dividing them, or I am meshing them. So I have the common point, the stiffness matrix of element 1 and 2 will be there at node 2. Contribution from element 1, contribution from element 2 will be there at the common node 2. So I am now adding the common node. It is called assembly. It's called assembly. And now I solve and I get the nodal displacement U1, U2, U3, U4. U1 is 0, we fix it. And U2, U3, U4, I calculated. Okay. And now U4 is the mass displacement, and I got 0.0355. Okay. I know the exact solution. The exact solution 0.0378. Okay. So there is, because I divided into 3 elements. If it is divided into 6 elements, 10 elements, 50 elements, 100 elements, I will see the convergence. So the exact solution is a complex logarithmic. I do 3 elements and I got the solution as 0.0355. Okay. Instead of 3 elements, if I made it into 6 elements, I would have had 6 elements. So I will see solution is improving. If I'm going to get 10 elements, still it's improving. And it is converging. As I increase the number of elements, I see the solution is converging. Okay. So as I claimed that elements increase is making the solution to converge towards the exact solution. So this is the solution I had by increasing the order of the polynomial refinement. From cubic 6th order to 10th order, how the solution. This is increasing the number of elements, 3 elements, 6 elements, 10 elements. Now I could see part element method is a combination of P refinement and H refinement. Okay. And now probably, I don't know how much. Of course, some of you are already refined on method, so it is a repetition for you. If you have understood up till this point, okay, you understood final method. Okay. Now, you may say, sir, you took the symptomatic problem and you solved it. The next one to do heat transfer problem. A cooling fin. The heat at one end is 700 degrees, is dissipated by conduction, convection. So the material is having conductivity coefficient and the environment is having convection coefficient. And conduction is taking place in the cross section, convection is taking place in the surface, perimeter. And the atmosphere, let's say, is 40 degrees. What will be the temperature? Now, the variation of the solution probably, okay. Now in heat transfer, with your little knowledge of heat transfer, if it is conduction, it's linear, dP by dr. If it is conduction plus convection, it is non-linear. And the convection itself, there are 2 types of convection, natural and forced convection. So if it is natural convection, convection is slow. If it is forced convection, convection is severe. So you will see the third curve where the temperature variation is exponential decay. So what is the exact solution? You don't know where you are. You don't know. Are you a forced convection or natural convection or somewhere in between? If it is going to be forced convection, what is the convection coefficient? So the exact solution is going to be nth order. Nth order. You cannot find out exact solution. But you need to find out the temperature at any point for you to design the thermal stress and for you to design the component, cooling fin component. What will happen if you don't cool the fin? You understand where is the cooling fin around the engine cylinder? There will be cooling fin to dissipate the heat, because when the fuel is getting burned, the temperature of the cylinder will be increasing. If you don't dissipate the heat, then the engine will cease. So you need to design the cooling fin in such a way the dissipation is efficient. You could make it efficient by changing the cooling fin material to aluminum or to copper, but copper is costly. So you are making an optimum design, optimum in shape, optimum in cost. So you need to find out an approximate solution. You need to find out an approximate solution. And you are going to get the same approximate procedure. You have to transfer your heat transfer problem into a mathematical problem. What you do in your taper rod problem in the first case for the dining room table, you wrote the governing differential equation by writing the equilibrium of forces, sum of your vertical force equal to 0. In your heat transfer, what are you going to do? Equilibrium is heat in equal to heat out. Heat in equal to heat out. So when you write the equilibrium equation of heat balancing, the governing equation is becoming like this. It has got the domain and it's got the boundary condition. What is the boundary condition? At x equal to 0, temperature is T0, high temperature, 700 degrees. And at x equal to L, if the end is open to atmosphere, conduction is equal to convection. If the end is insulated, conduction is equal to 0. Apply the boundary condition, suitable boundary condition, and find out the solution. Find out the solution. Okay, which Murugan will handle in the next afternoon. Okay. Now, if there is a fluid mechanics man here, now if you are going to write here flow equilibrium equation, you have a governing equation. If there is an electrical man here, you are going to write here magnetic flux equilibrium. You will have a mathematical equation. If there is a vibration man here, you are going to write here vibration equilibrium. If you are going to be acoustic man here, you are going to have a acoustic equilibrium. Okay. I think I'll come to my last slide and conclude. This heat transfer our man will take. So this is a heat transfer. I just want you to have a look at the equation, governing equation. And next is solid mechanics problem, which we did. d by dx of Ex dy by dx, gamma x equal to 0. I want you to look at the fluid mechanics equation. I want you to look at the electromagnetic equation. Now, this is in general. Every problem is defined by mathematically a differential equation. What differential equation? quadratic differential equation. You named it as electromagnetic, heat transfer, solid mechanics, flow, etc. But mathematicians put everything under one single equation called quadratic equation. That is that. Quadratic equation. Every engineering problem is put under one single mathematical equation, second order quadratic equation. You said my problem is heat transfer. Someone else, my problem is electromagnetic. Someone else, my problem is fluid mechanics. But mathematicians said, your problem is a second order differential equation. If you know how to solve a second order differential equation, heat transfer follows, you can solve your problem. Electromagnetic follows, you can solve your problem. Vibration follows, you can solve your problem. So mathematics put everything under one single equation called governing differential equation of order 2. Only thing they don't know what is the physical equation, but they could classify into mathematical equation, one equation. If you could solve that equation, you solve your engineering problem, mechanical engineering people, civil engineering people, electrical engineering people. So you should see mathematics has engulfed every engineer. Then you will ask me, sir, therefore is it only second order differential equation is all everything? I say yes, and I say no. Now with your centrometric knowledge, you will know that your beam problem, bending of beams, centrometric taught you, EI into d per 4 W by dx per 4 is equal to Q of x. What is the equation? Fourth order equation. Fourth order equation. So there are your mechanical engineering problem or your centrometric problem, fourth order. If you are going to have shell, it is eighth order problem. Eighth order problem. So far, you're talking about elongation in x direction, heat transfer in x direction. How about your contraction in the y direction, contraction in the z direction? We didn't bother. Simple reason. We said contraction y and z is small, we neglect it. But a stage comes, you say, no, I cannot neglect, I have to include it. So your problem from one dimension it becomes two dimension, from two dimension to three dimension. You will do it tomorrow, 2D. Okay. I don't know whether I have given clarity of your mind. Okay. I don't mind, after all, this is my notes which I use for my class. I don't mind sharing it with Murugan. You can have a look at it. Only thing, don't misuse it. Okay. You can use it for your own class. Okay. I'll give it to Murugan. And Murugan will continue on in the afternoon your heat transfer. I don't know whether it will continue on for the beam also. Tomorrow, somebody else will come and continue on with the two-dimensional plane. Okay. I hope I have laid the foundation for the finite. We're going to bring the step. Any physical problem can be represented by a mathematical equation by following the physics law of equilibrium, the respective. For solid mechanics, sum of your forces in any direction is equal to 0. Equilibrium of force. For heat transfer, thermal equilibrium, heat in equal to heat out. Like that for every domain. You have equilibrium. With that, you bring in your governing equation. Then you try to find an approximate solution by substituting an approximation and become better approximation by satisfying the boundary condition. When you substitute that better approximation, you get your governing differential equation is no more homogeneous, it becomes not equal to 0, there is a residue. You minimize the residue. You minimize the residue by Ritz method, that's your energy equilibrium. So the solution is going to be the energy equilibrium, which makes the solution to be best solution. So finite element became best approximation. In that, increase your number of elements, H refinement. Increase the order of polynomial, P refinement. Then you get improved result. Converge, you can be confident of your design. Give this confidence to your students so that he need not be panicky. He can do new things with that. I stop here. I'll keep a few minutes open for anybody to ask any question, and then Murugan will take over.
Thank you, sir. Thank you, Professor. So, participants, if you have any queries, you can unmute yourself and ask your doubts to the professor.
Yeah.
Otherwise, participants, you can type your question in the chat box also. I'll read the question. Professor,
How
one question.
Put the chat box question.
How a thermal spray of particles can be modeled?
Okay.
Thermal spray
Yeah,
of particles.
Yeah. I presume this gentleman is already using FEM for.
Yes, sir. Yes, sir. This is Dr. Kumaran.
Problems. And
Sir, your voice is not clear, sir. Sir,
medium has become both solid and liquid and gas. There is a spray. So, like you wrote, stress by strain is equal to Young's modulus. Similarly, your heat in is equal to heat out. Now, you need to write constitutive equation. Constitutive equation. The relationship, like you wrote, stress and strain related by Young's modulus E. Similarly, your heat transfer, you wrote in terms of equilibrium of conduction and convection. Similarly, now you have to write the medium to be combination of, it's a multidisciplined medium. So there is a constitutive equation which relates what is happening. So if you are going to look at the constitutive equation of a multi-medium, like solid medium, liquid medium, that constitutive equation, you'll be able to model the spray mode. Okay. Maybe a simple one I'll explain to you. You have your solid concrete, you have your clay, okay, building, okay. Now you are going to put a pile foundation on a clay soil. So the clay has to be modeled, clay has to be modeled by the constitutive equation. Is clay is a solid? Is clay is a liquid? So you have, how do you differentiate clay? It has got Young's modulus E, it has got rigidity modulus G, and also it has got the bulk modulus K. So your constitutive equation will relate all the three models, all the three modulus. Okay, that is symbol for a clay. Similarly, you will now find for the gaseous medium. You have constitutive equation. Put that constitutive equation, then everything is the same. Same procedure. Who are the gentlemen who raised the question? You can still have an opportunity to respond to me, whether you understood first. I didn't teach you how the constitutive modeling of a multimedia will be, but you understood that you are going to write a constitutive equation. This in terms of solid mechanics, it is by E. Okay. If it is going to be for solid and liquid, a clay medium, it is E, G, and K.
Yes, sir. Thank you, sir. I think we also responded this question, sir. Thank you.
Okay. Well, I'm available. You can send me the queries in case we have to my mail ID.
Yes, sir. Sure, sir.
And I will share this material with our Murugan.
Okay, sir. Okay. I will.
He can share you want.
Okay, sir. And the end of the program, we are going to share all the PPTs, sir, on the session to the participants.
Okay.
Yes, sir.
Okay. All right. Okay. Bye.
Sir, thank you, sir. Thank you
Okay, Raja.
for your fundamentals, sir. Thank you.
So thank you.